Hey guys, today we're going to talk about some issues that early helicopter designers face when designing the helicopter. Today we're going to talk about specifically the issue that the designers found when transitioning the helicopter from hover to forward flight. The issue of what would happen basically is the helicopter would roll and crash. So I'm going to talk a little bit about that real quickly about how that happens. So before we dive into that, I'm just going to define a couple things. We have the leading edge over here, which is the side of the blade that is going against the free stream velocity, and the retreating side, which is moving with the free stream velocity. All right, so let's define our velocities real quickly. We have our tangent velocity at 50 meters a second, and up here we have the same. And in real life, these velocities would be much greater, but just for explanation reasons, we're just going to choose a 50 meters per second. And we have the free stream velocity, which write that down too. All right, so the issues arise from the relative velocity of the free stream velocity and the velocity from the leading side and the retreating side of the blades. So here we have the velocities running into each other. So the blade would see a velocity that would add these two up. So on the leading side, you can add 50 plus 50 and you have your 100 meters a second, or your total velocity. And over here, since they're moving in the same direction, it's 0 meters per second. You can think about it like in a car. If you're driving head on, you crash into a car, one's going 50 miles per hour and you're going 50 miles per hour, and you're gonna experience a 100 miles per hour collision. And over here, if you're moving parallel, you're not going to collide because you're going the exact same speed in the same direction. So the velocity relative to each other is going to be 0. All right, so over here we're going to look at our lift equation, and it's lift equals 1/2 rho v squared times your lift coefficient and your lifting surface area. Now you can see velocity plays a large role in how much lift is generated in a airfoil. So here we see we have 100 meters a second, which is going to generate a lot of lift, and here we have 0, which is going to generate 0 lift. So if we come over here, here's our blades looking onward as the helicopter is flying straight toward us. We have, this is the lift slope. All right, so we have quite a bit of lift over here and 0 over here. So maybe I'll just call this lift X. And we have, on the leading side, it's apparent that it's a lot of lift over here, generate a lot of thrust. And since there's not near as much on the opposite side, on the retreating side, what's going to happen is there's going to be a moment created here. And that in turn would cause the helicopter in forward flight to twist or roll and crash. And what the early designers did and how they fixed that issue was they put hinges right here and right here, which allowed the blade to flex up like so, and in that way counteracting, or not counteracting, excuse me, but eliminating the moment, but still maintaining the force or the thrust required to keep the helicopter in flight. Thanks very much.